Hey guys, welcome back. This is Frank, and welcome to our IGCSE CoSci Physics revision videos. Our current unit is P4 Light and EM Spectrum. So today, the video is going to be a quick one. I'd like to talk a little bit about refraction. So, first of all, starting with the definition of refraction, we know that refraction is the change in direction of light when it passes from one material slash medium, whichever you prefer, to another. Okay, so refraction is the change in direction of light when it passes from one material medium to another. So direction, the most obvious way to measure direction is if we measure the angle of the rays to the normal. So I'm just gonna quickly do this here. Let's say we're given this scenario. We have an angle of incidence of 25 degrees. And we know that the angle of refraction here in this, let's say this is a glass block. So the angle of refraction in this glass block is gonna be, let's say, 15 degrees. Okay, and then we know that the angle of incidence here is 15 degrees as well, because, well, apparently this is 15 degrees and this is also 15 degrees. So this is going to be 25 degrees. And an interesting fact to notice here is that, the ray comes out sort of like parallel to what it has been before. So this can be very useful when they give you something like this. So if they have like here two parallel rays and then they put some apparatus here and then it comes out something like that, and they ask you what apparatus that is, that's probably going to be a glass block. So you know that it's going to come in and come out parallel because, well, the refractive index, we're going to talk about that later. The refractive index of the glass block is the same. So, the bigger the incidence ray in air, the less the the refracted ray, the angle of refraction in the glass block, and vice versa. All right. So now let's talk a little bit about the rules, some of the general rules of refraction. So something that I usually find very useful is I'm pretty sure you've heard of this acronym, TAGAGA. So basically, what TAGAGA means, TAGAGA stands for. Let me use another color. TAGAGA stands for towards. Let's just write this out first. TAGAGA. So, towards, air, glass, away, glass, air. So basically, it's describing two situations. If, let's say, you have a light ray shooting from air, this is glass, air to glass, basically it's gonna be towards, and we're talking about towards and away from the normal. So let me just point that out here. This is a normal. So remember that a normal is just a perpendicular line to the surface of this glass block, and it's at the point which the ray hits the glass block. So this is normal. This is normal. So in this case, that's the normal, and we know that it's gonna be towards the normal. So if the incidence angle is normal, say, if the angle of incidence is like 25 degrees in this case, you pretty much know that the angle of reflection is gonna be, sorry, the angle of refraction is gonna be less than the angle of incidence. So this is towards air glass, and away glass air is exactly the same, just the opposite uh, of towards air glass. So let's say you have a glass block over here, and then you have a ray shooting from, it probably came from the air and then went into the glass, but whatever. And you know that, let's say this angle is 25 degrees. So what you would know is that, the angle of refraction here, this angle is I, this angle is R. The angle of refraction here is going to definitely be larger than the angle of incidence. So it kind of bends away from normal. You can say that. Okay, next I would like to talk a little bit about refractive index. So what exactly does refractive index mean? So the refractive index of a material is, is used to describe uh, the change in velocity of light in that material. So basically, what this means is that, let's say it is defined by this equation. So we usually use n to denote the refractive index. So n equals c divided by v. What this means is that the refractive index is equal to the velocity of light in space, in a vacuum over the velocity of light in that substance or in that medium. So a very useful thing to remember here is that, the velocity of light is the velocity of light in vacuum is 3 times 10 to the 8th meters per second. So that's c. So that's a constant usually used in physics, and you need to remember that pretty much because it's very common. So the velocity of light in vacuum over the velocity of light in medium. So let's look at a practical example. Let's say you have the speed of light in a glass, let's say, is 2 times 10 to the 8th meters per second. And I'm using velocity and speed interchangeable here, because they're pretty much the same as far as what we are considering in this unit. But you have to know that velocity has a direction apparently, and speed doesn't. And velocity is a vector. We learned that in P1 in motion. So yeah, but I'm using speed here just because it's easier. But you should know that velocity and speed are not exactly the same. Anyway, so we have 2 times 10 to the 8th meters per second. That's the velocity of light in, I don't know, a certain type of glass. So it's asking what is the refractive index of that glass. Well, using our equation, very simple equation, we know that the refractive index equals to the velocity of light in vacuum over the velocity of light in medium. So we can just write 3 times 10 to the 8th meters per second over 2 times 10 to the 8 meters per second, which gives us 3 over 2 and 1.5. So a few key takeaways here. First of all, you notice that n equals to c divided by v, and c is the largest velocity you can get, pretty much in all physics. So you cannot surpass the velocity of light. That's a common rule in classical physics. So the velocity of light in a vacuum. When I say velocity of light, I'm usually referring to the velocity of light in a vacuum. So the velocity of light in a vacuum is so large that pretty much any velocity of light in any medium except air is going to be lower than it. So if you think about it, air is a very not dense gas, and although it's not exactly the same as a vacuum, the difference is so small that we usually ignore it. So we usually take for granted that this is also the velocity of light in air. So I'll just note it down: air and vacuum. Um, and if you have a liquid, or let's say a solid, it's definitely gonna be denser than air. So the velocity of light in those mediums are definitely gonna be smaller. So an interesting property of n to remember here is that n is always gonna be bigger than 1, because, well, apparently C is always going to be bigger than V, as I've explained. So it's a useful way to check. If we got an n less than 1, that means we were probably doing something wrong. And also, um, you have to know that n does not have a unit, so it's not. If you see here, it's meters per second over meters per second. So apparently we have no unit for n. It's more like a ratio, I'd say, because it's a refractive index. It's an index. It's not an actual value because it's relative to the velocity of light in vacuum. Another thing about TAGAGA that I forgot to mention is that it doesn't only apply to air and glass. It also applies to any when light travels from any less dense medium to a denser medium. So if you replace this with, let's say, water and glass, or air and water, or whatever, it's still gonna work. So as long as it's traveling from a less dense medium to a more dense medium, it's towards. And when it's traveling from a more dense medium, a denser medium, to a less dense medium, it's away. That's just something I would like to point out. Okay, moving on. Next thing I would like to discuss is what we call Snell's law. So what exactly is Snell's law? Well, this is how it's written on our syllabus. So it's like n. Okay, I'll change the color. N equals, all right, sine theta I over sine theta r, or you'll see it like sine I over sine r, which is basically the same thing. So sine theta I over sine theta r. So that's pretty much a simplified version of the actual law. So you don't need to know that, but I think it's good to know because it helps you understand. The full form of Snell's law is like this. So n1 sine theta 1 equals n2 sine theta 2. So it describes the relationship between the refractive index of indexes of two materials, and the angle of incidence and the angle of refraction between them. So let's say the reason why we are given this equation is because we know that, as we said here, air and vacuum has pretty much the same velocity. Light travels at pretty much the same velocity in both air and vacuum. So the refractive index of air is usually just 1. So if, let's say, the first substance is air, it's just sine theta 1 equals n2 sine theta 2, and then you rearrange it to become sine theta 1 over sine theta 2. So the reason why I'm introducing this is because, so that the limitation of this form of the formula, because first of all, this one only applies to air, because as I've explained, it's only when n1 is 1 when you can use this formula. So only in air would the n1 be 1. So applies to air only. I'll just write it as air only. And number 2, as you can see, it's sine theta 1 over sine theta 2. So the restriction on that is that the angle of incidence must be in air, and the angle of refraction must be in that substance. So let's say you have a glass block with angle of incidence for like 25 degrees, and this is 15 degrees. And well, you can only use sine 25 degrees over sine 15 degrees to find the n glass. So to find the refractive index, you cannot flip it the other way around, because otherwise that's gonna give you like a wrong an incorrect result. And you can actually tell if you did it wrong, because apparently n is going to be larger than 1. And if you flip this around, n is definitely not going to be larger than 1. So bear that in mind when you're doing problems. It helps you correct. So a preferable version, I'd say, of this formula, which I prefer, looks something like this. So n equals sine theta air over sine theta substance. So even if they give you like the substance and didn't give you air, you still know that air is going to be on top. So it's pretty useful if you want to solve this kind of problems. Anyway, so this is the equation that I recommend you to remember. And now let's do some real life problems. Let's just take our example over here. This is this 25 and 15 example. So we know that theta I. Let me change the color. We know that theta I is 25 degrees and theta r is 15 degrees. So this is in air and this is in glass. And now we would like to calculate the refractive index of the glass. So n, we say, is equal to sine air, sine theta air, over sine theta sub. So we know that it's going to be sine 25 degrees over sine 15 degrees. Which, if you calculate a bit on the calculator, gives you something around approximately equal to 1.63. So that's actually way off, than what is actually the refractive index of glass, because I just used a random number here. But in the test, you should get something around like 1.53 for glass and 1.33 for water. You don't have to remember them, but it's around that range, so you kind of get the idea of how big the refractive index should be. And also, a fun fact to know is that the currently known substance with the largest refractive index is diamond, which I believe has a refractive index of around 2.4. So you know that your n is definitely gonna be somewhere around 1 and 2.4. So that's useful to remember when you're doing a test. If you got something like 3.6, that's definitely gonna be incorrect. So those are some of the key points of refraction. So to sum up, we talked about TAGAGA, change in direction. We talked about refractive index and how to calculate refractive index. We talked about Snell's law and where it came from, and how to calculate based on Snell's law. So yeah, that's all for today. Thanks for listening, and I hope this video helped you.